Now I'm going to talk about the optimal global thresholding using the analytical method. So first of all, we have to consider our distribution as a mixture of two distributions that are typically Gaussians. This is our probability density function, Pz, and it's made out of two distributions. This is the first, and this is the second, P1z and P2z. So just to make things clear, I'm going to draw each of these distributions independently. So I'm going to get this graph for P1z, close enough, and this graph for P2z. Okay, so this is the z-axis, which represents the intensity level. This is P1z, and this is P2z. So to make things clear, I'm going to assume that this distribution here is associated with the object. This is the object, and this is associated with the background. Now I explained previously that no matter in this kind of distributions, no matter where I choose the threshold, I'm gonna get an error. So what I can do in this case is just try to minimize this error. Therefore, I want to establish an expression for that error mathematically and try to minimize it. So let's say that I have a threshold here. I can project that on the two graphs. Okay, so this is T. Now, what we have to know first is that everything above the threshold is going to be classified as this is the maximum value, 1. So everything above the threshold is going to be classified as a background, and everything below this threshold, below or equal, is going to be my object. Now, given that, what's going to happen here is that this proportion here is going to be misclassified as a background. Okay, so remember that this is the probability density function of the object, so everything here in this distribution is an object, but if I set a threshold here, this proportion is going to be classified as a background and misclassified as a background. This is wrong. Okay, so similarly here, everything here in this distribution is a background, but given that thresholding, this proportion is going to be misclassified as an object. This is misclassified as background, and this is misclassified as an object. Now what I want to do is just to try to estimate these proportions, and we can do that very simply by integration. So I can say that the first error, this proportion here, is going to be denoted E1t. Okay, before expressing it, let me just tell you that it represents the misclassified, the proportion or the percentage of misclassified pixels from object pixels. Okay, so E1t is going to be equal to the integration from t, okay, the integration from t to plus infinity of P1z dz. Okay, so similarly, E to t denotes the percentage of pixels the percentage of pixels misclassified as object, okay, from background pixels. Okay, this is the percentage of pixels misclassified as background, okay, from object pixels. I hope this was not too confusing. Now, what I want to find is, I'm looking for the percentage of misclassified pixels from the entire image. So now the mistake is to go and say, well, this percentage, which is denoted by ET, is just going to be equal to E1t plus E2t. So this is a mistake because this percentage is not a percentage from the entire image. It's rather a percentage just from object pixels. And the same thing, the same principle is true in this case. This percentage is just the percentage of misclassified pixels from the background pixels, not from the entire image. So we have to transform this percentage here as well as this percentage here to represent a percentage of misclassified pixels from the entire image, and for this reason I have just to multiply here by P1. Okay, so what is P1? P1 is just the proportion of object pixels, and here I have to multiply by P2, which is just the proportion of background pixels. So in this case, this term would represent the percentage of pixels misclassified as background from the entire image, and here I'm gonna get pixels misclassified as objects from the entire image, and then I can say, well, this sum is gonna give me the percentage of misclassified pixels from the entire image. Okay, so now what we need to do is to minimize this equation, and this can be done by a method called Leibniz's rule. Okay, so Leibniz's rule which is based on differentiation, tells me that in order to minimize this, I have to get P1, P1z, or rather P1t, let me write that again, P1 multiplied by the density P1t, okay, this is its threshold, must be equal to P2 multiplied by P2t. Okay, this is the condition to get this equation or expression to be minimal. Now, before solving this, of course, we assume that we know the this expression, okay, the probability density function P1z as well as P2z. So these are required to solve for this equation. So one thing that we can do in the beginning is just to assume a given distribution or a given form for these two functions, and typically we assume that they are just Gaussians. Okay, therefore if I assume that these two functions are Gaussians, then I can write my function pz as p1, okay, multiplied by 1 divided by 2p square root of sigma 1 multiplied by exponential of the mean of the first distribution minus z, this is squared, divided by 2 sigma 1 squared. Okay, so this is just the first distribution function. Then I should add p2 multiplied by exponential 1 by 2p square root sigma 2 by exponential of mu1 mu2 minus z squared divided by 2 sigma 2 squared. Okay, and if I replace this, this is the second distribution function. Okay, and if I replace this in this equation, in the previous equation I showed you, this one, okay, the solution we are gonna get is gonna be in the form of a quadratic. We are gonna get rather a quadratic equation. Okay, and this term and this term and this term are expressed in with respect of mu1, mu2, sigma 1, sigma 2, p1 and p2. Okay, and the solution of course is going to lead to two solutions because it's a quadratic equation. This means that we are going to have two optimal thresholds, but in some cases it is possible to do some simplifications. For example, if I know that these two are equal and these two are equal, then the threshold is simply mu1 plus mu2 divided by 2, but this is usually not the case, and we have to establish these parameters to solve this equation. Otherwise we cannot find an optimal threshold. Okay, so now how to find these parameters? This is the question. Well, we have to minimize another equation, and this equation is just the difference between the estimated density function pz, okay, and the actual density function, which is nothing but the histogram. This is a given information that we can get from any image whose pixel values are known. So in order to identify these parameters, we have just to minimize a function called error mean square. Okay, so this error must be minimized, and this error is just the difference between the estimated probability density function pz at the intensity level I, okay, minus the histogram at the same intensity level. Okay, so I'm just like trying to compare the distribution established from the actual distribution. So this is the meaning of that. I'm gonna take the square of that, okay, and I have to find this error for all possible intensity levels. Okay, therefore I have to sum that from I equal to 1 to n, such that n is all possible intensity levels. Okay, and in order to find this is the error, the total error, and we have to find the mean. Okay, the mean we have just to divide by n. Now the problem is that analytically it is impossible to solve this. Okay, therefore we resort to some numerical methods that try to establish or try to evaluate this error for different values of these parameters and see where the error is minimized. Okay, and in this way these parameters can be established, and some of these one of these methods that can be used to find these parameters, numerical methods, are conjugate gradient or Newton technique. Okay, so we have to pass from all of these mess just to find an optimal global threshold. So now in the next video I'm gonna talk about Otsu method to find an optimal threshold, and it's far less messy than this complicated technique.